Hello Math 1324 students, let's begin Lesson 3, Functions and their Graphs. Section 1, Functions. What is a function? I'm afraid I cannot answer that question yet. We will answer, but way down here in subsection 1.5. Until then, we need a lot of preparations to do. First, Cartesian products. Let x and y be non-empty sets. The Cartesian product x times y is defined as a set of all possible ordered pairs, small x comma small y, where small x and small y are members of capital X and capital Y. Here are some examples. If my first set is 1, 2, 3 and my second set is AB, then the Cartesian product x comma y is 1a, 1b, 2a, 2b, and 3a, 3b. That covered all possible ordered pairs. Is there any more? Not really. There are 3 elements here, 2 elements there. 3 times 2 is 6, and I covered all 6. No more. What if we have 2 infinite sets, such as x is r, y is r, horizontal line, vertical line, and then x times y, we have coordinate plane, and all the points on the plane correspond to x times y here. By the way, this kind of coordinate is called Cartesian coordinate, associated to the same Cartesian, named after French mathematician Descartes. Okay, now that we have Cartesian product, we can define a relation. Any subset R, rather any non-empty subset R of the Cartesian product is called a relation. If an ordered pair x comma y belong to that relation R, then we say x is related to y. Term related to is not that important, but please remember the relation. Any non-empty subset of a Cartesian product, then that's a relation. So we can define any kind of relation haphazardly. Any subset will do, but if that relation has nothing to do with algebra, then what's the point? After all, this course is about algebra. So we are not going to consider those kind of relations. Most of the time, or to tell the truth, all the time, we are going to consider relations associated to some algebraic equations like this. X squared plus y squared is equal to 1. Or like this. Another equation, x squared minus y squared is equal to 1. And then still more example, y equals x squared. Of course, there must be many more, uncountably more. But in any case, we're going to stick to relations obtained by some algebraic equations between x and y. For that reason, many times people call these equations as algebraic relation. But in the most strict sense, the term relation is a little bit broader because it is possible to define a relation that has nothing to do with the algebra, except that those kind of relations are totally useless for our purpose because this is an algebra course. Okay, let's look at the first relation a little bit deeper. It turns out the first relation is the circle. X squared plus y squared is equal to 1. It's a circle centered at the origin with the radius 1. Here's an example. X comma y is 1 comma 0. This point here, and as you can see, it's on the circle. It belongs to this relation. You can check. 1 squared plus 0 squared is 1. Yes, indeed. Here's another example. X comma y is 1 comma 1, and that point is over here, and as you can see, it doesn't belong to the circle. So it doesn't belong to this relation R1. You can check manually. 1 squared plus 1 squared is supposed to be 2, not 1, so this one is out. Want to see another example? Okay, here we go. X squared minus y squared is equal to 1. We have this hyperbola. 1 comma 0 is this point here. Yes, it belongs to this hyperbola, and you can check it. 1 squared minus 0 squared is 1. Yes, indeed. How about this one here? X comma y is 0 comma 1. 0 squared minus 1 squared is supposed to be negative 1, not 1. So that's out. As you can see here, this red point does not belong to this R2. It's not on this curve. It's not in this relation. Here's a third example. Similar. This time y equals to x squared. You can check manually, right? Alright, those are examples of relations. Now that we have some relations, let's consider the next concept, domain and range. Basically, the domain is the set of all x values that are related to some y. The range is a set of all y values that are related to some x. Now, if you're not really understanding this logical statement, that's okay. The key idea here is set of all x for domain, set of all y for range. Let's solidify our understanding through some examples. First example we saw before, R1. What's the domain and what's the range? Well, look at the x-coordinate. -1 all the way to +1. Do you see it? Beyond +1, I see nothing. Beyond -1, I see nothing there either. So the domain is -1 to +1, and same goes to the range. Nothing down here, nothing up there. Everything is between -1 and +1. Do you see that? The domain and range are both -1 to +1. How about the next example? Look at the graph and tell me. The domain, well, from 1 to infinity, yes, okay, we have these curves, either this way or that way, just going on to the right forever. So 1 to positive infinity are all covered. -1 to negative infinity, or more precisely speaking, negative infinity to -1, they will cover too. This way, that way, just going to negative infinity all the way to the left. But in the middle, I don't have anything. How about y-coordinate? Y-coordinate looks like everything is okay. Any y-coordinate value going up forever, going down forever, yeah. Indeed, we have these as domain and range. Negative infinity to -1 coming from this left-hand side curve piece, and then 1 to positive infinity coming from the right-hand side piece. And then between -1 and +1, I have nothing. Range, I don't have any gap. Do you want some further visualization? Okay, here you go. Consider these vertical lines. The vertical lines share the same x-coordinate values. Now, from here, from 1 to positive infinity, all those vertical lines have crossings. Cross this curve here or there twice. In this case, just once. In any case, they are crossings, which means these x-coordinate values here is related to some of those y-coordinate values, either here or there. So they belong to the domain. Same goes over here. But between -1 and +1, no crossing. No y-coordinate. So they are out of domain. How about the range? We can do the same thing with horizontal lines. Horizontal lines share the same y-coordinate, and same y-coordinate, and this x-coordinate and that x-coordinate. These two x-coordinates are related to the same y-coordinate. In any case, each of these y-coordinate is related to some x, either right or left. So everything is in the range. How about the third example? Domain and range? Well, this curve, it goes on forever to the right and also to the left, so negative infinity to positive infinity all covered. That's the domain. And the range, they go up forever, but do not go down, so from 0 to infinity. Pretty clear, right? Indeed, domain and range. Any question here? Want to check out even further? Well, you can consider all these vertical lines because vertical lines share the same x-coordinate values. No matter what x-coordinate I select, we do have crossing. So this y-coordinate value is related to, this x-coordinate value is related to this y-coordinate. This one is related to that, and so on and so forth. Range, on the other hand, we can use horizontal lines. All these y-coordinate values greater than or equal to 1, greater than or equal to 0, all those, we have at least one crossing, which means this x-coordinate value here is related to this y-coordinate, and so on and so forth. But if y is negative, no crossing, nothing down there. So they are outside the range. You can use those vertical lines and horizontal lines and crossings to solidify the idea of domain and range. Next, finally, we are ready to discuss functions. But then again, it's going to be a long story, so let's stop here and let's resume our discussion from 1.5 in a second video. Stay tuned.